Okay, let's review some basics for parallel plates. To begin with, I've got two metal parallel plates. Here's one overdrawn in black. Here's one also overdrawn in black. A wire, and then I've got this thing that's the battery. And the battery looks something like this. It can be, let's see, there's a line, long, short, or I could draw it reversed, short, long. It can go in any direction. The long side is the positive side, so you can see how I have the battery reversed. And this connection up here, I've got the long side on the left, short side on the right. So on the positive side, that means this wire is positively energized, and this is positive. So that's where all the positive charges are going to be. On the negative side, that's where all the negative charges are going to be. So in this, it's going to generate an electric field. I have two equipotential surfaces. So the two metal plates are at the same electric potential. That electric potential would be what the battery is. So let's say the battery is 20 volts, and the other side where it's negative, we'll call that 0 volts. What's important is that the difference in the two sides is what we're after. And so the difference is 20. So it's easy to do the math. If we just call it 0, then we don't have to worry about the delta sign anymore. All right, so the path between our electric potential. The electric field goes from high potential to low potential, or another way of saying it is it's the path a positive particle would take. So if I dropped a positive particle between the plates, it would be repelled from the left plate and attracted to the right. So my electric field would look something like this. And our electric field is going to be symmetrical, so our lines will be evenly spaced. We're going to ignore any kind of edge effects. It would look something like that. So that's the direction of the electric field. Now we need to do some things to find the magnitude of the electric field. To find the magnitude of the electric field, there are a couple things we can do, depending upon what we know. If we knew the force and the charge that's dropped between the plates, we might be able to do a little bit. Ooh, that's way wrong. So I know that F is equal to Q times E. So if I dropped a charge between the plates with some kind of value Q, and I could measure its force, I could find the electric field. That'd be the magnitude. I could also use this. V is equal to E over D. So if V is equal to E over D, the voltage, that's going to be 20 volts in this case, right there. And the distance, well, that would have to be given. So somewhere there'd be something else here that would tell me the distance between the two plates. And then I could find the E field. And when I do that in terms of units, that's going to be units of a volt over a meter. Whoops, a volt over a meter. So that can give me the magnitude of the E field. So that's magnitude and direction. Now let's look at work and changes of energy. So here's my setup this time. It's very similar to what we just had, but what's different is the batteries have been reversed. So there's positive and there's negative. So this is the plate with the positive charges on it. This is the plate with negative charges on it. Now we're going to assume our plates are the same size. So really the number of charges on each one would be the same. So I'll make it look at least the same there. So the value of Q on each plate would be the same, but we're just going to call it Q in any equations we have. All right, so how much work is done as a charge moves from one plate to the other? Well, the work, again, this is just a review, is equal to QV, or really Q delta V. So whatever my voltage is on the battery, the positive side will be the positive voltage, say 30 volts, and the negative side we'll call 0. That just makes the math easy, and that's why we call it 30 volts there for the potential difference. The electric field goes from high potential to low potential, so that's from the positive plate to the negative plate. You can also think of it as the path a positive particle would take. Now the work that's done is just Q, and Q would be the amount of charge that's dropped between these plates. So let's say it's a Q and the charge is equal to a value of whatever 4 protons is. So that would be the amount of work that's there, and V is the voltage. So one way to find out is to put W in here and say, well, W is equal to Q, which is 4 times 4 protons. So that's the charge on each proton times 30 volts. And that would give you an answer in joules. But there's a quicker way. It's with a smaller unit of energy. What I can do is I can look at the number of charges equal in magnitude to an electron. A proton is equal in magnitude to an electron times the voltage. So that would be 4 times 30. So I could look at the work as this, as 4 times 30. And what's different is the answer this time is in EVs. That's electron volts. So it's a really small unit of energy. 1 EV is equal to 1.6, that's the charge of an electron, times 10 to the negative 19 coulombs. That's the charge of an electron. Except it's not coulombs, it's joules. So 1 EV is equal to 1.6 times 10 to the negative 19 joules. Wow, 16 million millionths of a joule. That's a really, really small energy, unit of energy. But it's easy math. Okay, so how might we use something like this? All right, so let's suppose that we have a charged particle on the outside. A little different problem. I'll keep my setup just so it's kind of all together up here, and I don't have to really worry too much about that. I'll get rid of this. I'll get rid of the E field for the moment. All right, so let's say I have a charge out here equal to a value of 3 electrons. So that's the net charge on this particle, and of course I'm drawing it really big. And the particle is moving in here with some small amount of unit of energy. Let's say it's 200 EVs of energy. That's kinetic energy as it moves across. So as it enters the region of the plate, I want to figure out eventually how much energy it's going to have over here on the right-hand side. That's what I'm looking for. So as it goes between the plates, I need to figure out if this charge is going to gain or lose energy. So it's negative. It's equal to the charge of 3 electrons. The opposite plate is positive. Since the opposite plate is the opposite sign, it's going to be a gain of energy. Now the question is, how much does it gain? Well, it gains an amount equal to the work. So we got this new unit, the EVs. So that's going to be, in terms of work, that's going to be 3 times 30. So 3 times 30 is 90. So that means that it's going to gain 90 EVs of energy. All right, so here's what I have. I have 200 EVs gain 90 EVs, so 200 gain 90. That means over here it's going to have 290 EVs of energy when it hits the other side. Now I can go one step farther. If I know the mass of the particle, if I know that, then I know that this energy on the other side is going to be the kinetic energy. So that's 1/2 mv squared. So I could actually calculate the velocity. I can use that energy of 290 EVs, but I'm going to have to convert it to joules, so I got to multiply it. And that's equal to 1/2 the mass times velocity squared, so I could solve that for the velocity itself. So the velocity is going to be equal to 2 times the kinetic energy on the opposite plate divided by the mass. All that would be square rooted.